Hello, my name is Meng Duck, and today I'll be presenting the research I conducted in collaboration with Sui, Christopher, and Lawrence titled Co-Design and Evaluation of Visual Interventions for Head Posture Correction in Virtual Reality Games. Recent advancements in virtual reality gaming, VR gaming for short, have led to its commercial success in applications in education, medical simulation, and phobia treatment. However, extended VR gaming sessions can cause neck strain and discomfort due to the headset's weight, ranging from 400 grams to 800 grams. Additionally, VR users, like office workers who spend long hours at screens, may develop improper posture due to a lack of awareness and the immersive nature of VR. This issue is further exacerbated for individuals with pre-existing posture problems. These challenges underscore the need for solutions to detect and correct improper posture in VR. Researchers explore posture detection techniques, including pressure sensors on chairs for sitting postures and wearable sensors or full body tracking system for standing posture. However, these methods are often impractical for VR gaming, as chair-based sensors are unsuitable for standing users, and wearable sensors or full body tracking systems require expensive and intrusive hardware. With regard to posture correction, techniques have mostly been studied in office work, ranging from intrusive methods like pop-up notifications to more subtle approaches like ambient displays and slow robots. While posture correction has been studied in VR office work or through VR exercises, posture correction in VR gaming remains largely unexplored. This research aims to address the lack of solutions for detecting improper standing posture and providing corrective feedback during VR gameplay. Therefore, we focus on three key questions. First, how can we leverage data from VR headsets to detect improper posture during VR gameplay? Second, what are effective designs and posture correction interventions in a VR gaming context? And third, to what extent do our proposed interventions improve user posture during VR gameplay? To explore the first question, we use a Meta Quest 1 VR headset to develop a posture management system that detects improper posture and delivers visual interventions to prompt corrections. To investigate the second and third questions, we conducted two studies: a co-design workshop where participants helped brainstorm and refine posture correction interventions, and an evaluation study where the refined interventions are assessed on their effectiveness. Our system detects two types of improper head posture in VR gaming: forward head posture, marked by excessive downward head tilt, and slouching, characterized by a lower headset position relative to the user's calibrated upright height. We target these issues because they are prevalent in healthy individuals and can be easily detected using the VR headset's IMU sensor data. In particular, forward head posture is measured by the headset's downward tilt angle, while slouching is identified through deviations, referred to as normalized height, from the user's height established during an initial calibration process. To validate our method, we compared our height measurements with a high-precision laser tool, finding an error of just 0.031%. Similar to prior studies in posture using threshold-based detection, we ran a pilot study to determine that a head tilt angle exceeding -10 degrees or a height drop of more than 2 centimeters reliably indicates improper posture. To account for natural movements, we only classify posture as bad if these thresholds are exceeded for over 3 seconds. For posture correction, we drew inspiration from previous ACI research to design 4 visual interventions, ranging from explicit alerts to more subtle cues. The icon intervention uses posture indicators with color-coded feedback, where the green icon signals good posture and varying red intensities indicate misalignment. The grayscale intervention momentarily desaturates the screen when improper posture is detected, restoring color once corrected. The moving ball intervention encourages users to align their posture by following a vertically ascending red ball that turns green upon correction. Lastly, the circle field intervention introduces an interactive challenge where users must align a moving dot with a stationary target circle to maintain good posture. To iterate on these visual intervention prototypes, we conducted a co-design workshop with 9 participants experienced in UX/UI design, VR programming, or kinesiology. 6 of them played VR games. To ensure a diverse experience in each session, participants were divided into 3 groups, with at least one experience in kinesiology and one in either VR programming or UX/UI design per session. Participants first brainstorm and sketch their own posture correction intervention ideas. This sketch shows the participants' pop-up notification design. Next, they experienced our proposed interventions in VR and completed a survey rating each one's intuitiveness, intrusiveness, and likelihood of future use. In a second brainstorming session, participants propose new ideas or refine their initial designs based on the VR experience. For example, the same participants who originally sketched a pop-up notification later design a posture indicator. Group discussions follow each brainstorming step, exploring strengths, trade-offs, and improvements. We collected video recordings, design sketches, and survey responses for analysis. We found that the icon intervention, though the most intrusive, was rated the most intuitive with the highest potential for future use. Grayscale was seen as the least intrusive. Moving Ball had the lowest rating for intuitiveness and future use, and Circle Fill was discussed to be too similar to Moving Ball. Feedback highlighted that participants liked the icon's simplicity, but found it too distracting, while Grayscale was subtle but needed adjustments to avoid interfering with VR graphics. Based on these insights, we dropped Moving Ball and Circle Fill and refined the interventions, simplifying icon and adding smoother intensity to Grayscale. With the refined interventions, we conducted a control experiment to evaluate the effectiveness of each intervention in improving standing head posture during VR gameplay, compared to a control condition with no intervention. The independent variable was the intervention type, icon, grayscale, or control, while the dependent variables included head-tail angle, normalized height, duration of improper posture, and frequency of intervention triggers. Based on our goal to determine whether interventions during VR gameplay improve these posture metrics, we formulated the following hypothesis. H1 interventions will reduce participants' level of forward head posture, as indicated by an increase in head tilt angle. H2 interventions will reduce participants' level of slouching, as indicated by an increase in normalized height. H3 participants will spend less time in improper posture when interventions are deployed. H4 the actual number of times each intervention is triggered would be less than the number of times they would have been triggered in the control condition. 18 participants were recruited with no history of postural abnormalities. The study employed a within-subject design, with participants completing a target selection task that simulated a VR gaming experience for 10 minutes in each condition. During this time, posture data was collected and pre-processed to remove outliers. After each condition trial, participants answered a quick survey similar to the co-design workshop one to provide Likert scale ratings on intervention intuitiveness, non-intrusiveness, and future use. A post-study questionnaire was also conducted to gather participants' overall feedback on their preferred intervention. Analysis showed no significant differences in head tilt angle across the conditions, rejecting H1. The icon and grayscale conditions led to higher normalized height compared to control, supporting H2. Additionally, the grayscale condition reduced the duration of improper posture compared to control, confirming H3. The number of times the interventions were triggered did not significantly differ across conditions, rejecting H4. With regard to Likert scale ratings, the icon intervention received higher feature usage and intuitiveness ratings compared to the grayscale intervention. However, there was no significant difference in non-intrusiveness between the two conditions. The post-study questionnaire revealed that most participants preferred the icon intervention, citing its clarity in promoting posture awareness over the more subtle grayscale intervention. Based on the results and feedback from both the co-design workshop and the evaluation study, we propose several design guidelines for posture correction interventions. We recommend balancing intuitiveness and intrusiveness with simple, familiar designs like icons or legible text for explicit feedback and subtle background changes for implicit feedback. These approaches, effective in managing slouching, should be applied carefully, especially in fast-paced games to avoid disrupting gameplay. Customization is another key factor, as participants showed interest in adjusting intervention elements, such as icons and grayscale levels, to fit their preferences. This aligns with previous research highlighting the benefits of customization for higher user acceptance and satisfaction. Finally, gradual notifications with fade-in out mechanisms are also recommended, as they are more effective for behavior change than abrupt interventions. For limitations, the inability to manage forward head posture was due to task design favoring slouching. Future research should differentiate head tilt and slouching, adding audio and haptic feedback, and intervention should be made more inclusive for those with disabilities. In conclusion, this study introduces a novel posture detection framework and evaluates various posture correction interventions in VR gaming, demonstrating their effectiveness in improving posture. Thank you for listening to my talk.